All right, hello everybody. So in our last lesson, in our first unit, we're going to talk about Bayes' theorem and from a perspective of medical tests. So Bayes' theorem is just another way to look at compound events, specifically dependent events. So we're going to spend the first part of this video lesson just deriving Bayes' theorem, and then we're going to use it a couple times in some medical test examples. So let's dive in here. So if you recall from an earlier lesson, for dependent events, the probability of A and B was equal to the probability of A times the probability of B given that A has already happened. Along the same lines, we could also say that the probability of B and A is the probability of B times the probability of A, given that B has already happened. And those two things are equivalent. The probability of A and B, the probability of B and A, those are the same thing. If you put these together, you get the following. You get that the probability of A times the probability of B given that A has already happened is equal to the probability of B times the probability of A given that B has already happened. And if you do some rearranging here, so if you divide both sides by the probability of A, let's say, like so, these divide out on the left, and what you're left with is what we call Bayes' theorem. So Bayes' theorem, so I'm just going to add a couple things on here, just reviewing some terminology, says that the probability of B happening, given that A has already happened, is equal to the probability of B times the probability of A given B has already happened over the probability of A. Probability of B, probability of A, and P given it, or P probability of A given B, this is probability of A given that B has already happened. All right, and we're going to use Bayes' theorem in a specific application. We're going to look at medical tests, and specifically tests that give false positives and false negatives as well. All right, so in this example, we're going to look at a test for screening for breast cancer, a mammogram. So most tests to detect diseases, so whether it's like for STDs or for cancer screening or a virus or diseases like lupus or even drug testing in professional sports, most tests are not 100% accurate. Sometimes a test can give you a false positive, so saying that you have the disease when you actually don't, or a false negative, telling you that you don't have the disease when you actually do. So in this particular problem, we're going to specifically look at breast cancer from a perspective of women between the ages of 40 and 50. So the numbers I've used here I have pulled from an online resource. These kind of medical facts you can get with any like online journal. I've kind of made them nice round numbers for our use. So we're going to say about 1% of women between the ages of 40 and 50 have breast cancer. And that if they get a mammogram, they will test positive 95% of the time. A woman who has breast cancer, the mammogram will catch it 95% of the time, while a woman without breast cancer has a 10% chance of a false positive. So we're going to draw a diagram showing all the possible outcomes and the probabilities too. And we're going to calculate some of these probabilities as decimals and also as fractions out of 10,000. And I'll show you guys why that can be helpful in a few moments. So let's draw a little tree diagram here. So in the first slide, I'm going to draw my tree diagram moving left to right here. So a woman between 40 and 50 can we'll say they have cancer or there's no cancer. And the probability of having cancer we've established was 1%. So I'll write 0.01. And the probability of not having cancer would then be 0.99. And so let's say a woman takes a mammogram. There's two options. We'll branch out for each one. So the mammogram can come in and test positive or negative. Positive or negative. So let's look at the details in our question. So our question said, if a woman has breast cancer, the mammogram is going to catch it. It's going to test positive 95% of the time. So 0.95, 95% of the time, if somebody has cancer, it's going to catch it. And that means that 5% of the time, they're going to get a false negative, which means they have the cancer, but the mammogram won't catch it. Our question also says, if a woman without breast cancer takes the test, 10% of the time, they're going to get a false positive. So 0.1, 10% of the time, if a woman has no cancer, the mammogram is going to come back positive. So it's not a perfect test. Forgive me, that's our school's end of period bell. So you might hear some students in the hallways for a few minutes. That means they have a 90% chance of that it'll come back negative.
Jack Lee, could you please come to the office? Jack Lee, could you please come to the office?
So you can ignore that too. All right, so let's look at the probabilities we have in this table here. So from our first branch, we can see the probability that a woman has cancer and tests positive. That is 0.01 times 0.95. We're going to get that as a decimal, and we're not going to round that at all. We're just going to keep as much accuracy as we can. In this case, it might turn out to be to 3 or 4 decimal places, so let's do that. That's 0.0095. And I'm also going to just down below, as a fraction out of 10,000, that's 95 out of 10,000. So, if 10,000 women were to take a mammogram, what our math says here is that of 10,000, 95 of them will have breast cancer, and the test will come back positive. So let's repeat that for our other branches. So this is the probability that they have cancer and the test comes back negative. So that will be 0.01 times 0.05. And that's going to be 0.0005. That's 5 10,000ths. So 5 out of 10,000. And we'll keep going. So the probability that a woman has no cancer, but the test comes out positive, is going to be 0.99 times 0.1, gives a false positive 10% of the time. That's 0.099.
Could the following students please come to the office? Jack Lee and Olivia Bergen, could you please come to the office?
So forgive me, that's just the consequence of doing these videos in a school. So that's 990 out of 10,000. And we'll do that for the one remaining branch as well. So the final would be not having cancer and testing negative, which is the ideal thing. So that you don't have cancer and the test works. So times 0.9, 0.99 times 9, excuse me, 0.99 times 0.9. That's 0.891, which is 8,910 out of 10,000, squeezing all those guys in there. And you can add up those probabilities and make sure that they add to 1. And if you double check, you'll see they do add to 1. All cases are there. So now that we've analyzed all the possible outcomes and the probabilities, let's look at a couple things. Because what we're really interested in is, like, if you actually screen positive for breast cancer, what are the chances you actually have it? So let's look at part B here. What's the probability that a random mammogram gives a positive result? Well, there's two cases here, right? The probability of getting a positive result, well, that's the probability that, like, the person has cancer and tests positive, plus the probability that they don't have cancer and test positive. We calculated those two things. The first was 0.0095, and the second, no cancer and test positive, was 0.099. So we can add those two together. We get 0.1085. And it might also be helpful, you'll see why, to write that as a fraction over 10,000. So 1,085 out of 10,000 women will come back with a positive result. So let's look at part C. It's really, really worth asking. So if a mammogram indicates someone has breast cancer, what is the probability that they actually have breast cancer? So let's think about all the things that we've looked at here. So, and this is why we found these probabilities out of 10,000. It's going to be easier to frame this question. So of 10,000 women, here's what we've seen. 1,085 of them test positive. Of these 1,085 that test positive, only 95 of them, look at our diagram, of these people that test positive, only 95 of those people actually have breast cancer. And if we look at that, 95 out of 1,085, it's actually a fairly small number. If we make that into a percentage, with 8.8%. That's actually a very powerful result. Think about what this says. This is saying that if you test positive for breast cancer, there's actually only an 8.8% that you actually have the disease because of just the nature of tests, false positives and false negatives. So looking at, of these 990 plus 95, of these 1,085 women, you can see that most of them had a false positive. They did not have cancer and tested positive. So given out of these 1,085, only 95 had cancer, given that you test positive, there's only an 8.8% chance you would actually have cancer. And now these are rounded figures, but this idea holds true for many, many tests for viruses or diseases. So if you or a loved one actually, does test positive for, again, STD, or this can actually be applied to pregnancy tests as well, often you'll get tested again. or you might take another pregnancy test because of these reasons. We talked about Bayes' theorem on our first page of this note here. Let's verify this result using Bayes' theorem. So what we're really interested in is we're interested in the probability that a woman has cancer given that they've tested positive. We can use Bayes' theorem here. So using our formula from the front, this is equal to the probability that they actually have breast cancer times the probability that they tested positive given that they actually have breast cancer, divided by the probability of getting a positive test. And we have all these things. So in the initial setup of the question, we assume that 1% of women between ages 40 and 50 have breast cancer. The probability of a random woman having cancer, 0.01. The probability of testing positive, given you have cancer. So this is just kind of the success rate of the test. The question says that if someone has cancer, the mammogram catches it 95% of the time, so 0.95, divided by the probability that somebody tests positive. We found that in part B. We got 0.1085. So we had to find that out ahead of time, 0.1085. And if you guys do that calculation, 0.01 times 0.95 divided by 0.1085, you can see that Bayes' theorem gives us the same result. You get about 0.088 or about 8.8%. So whether you use a tree diagram and maybe think of like out of a big group of women, like 10,000, or whether you use Bayes' theorem, both methods get you to 8.8%. So really fascinating application of probability.